In this video, we'll end Chapter 5 by discussing the binomial distribution and some of its cool properties that can be used to calculate probabilities, means, variances, and expectations very quickly. First of all, we need to discuss what a binomial experiment is. A binomial experiment is a probability experiment similar to the ones we've talked about before, but that has another couple conditions. First of all, we need to know exactly the number of trials ahead of time. So are you going to try this 30 times, 3 times? It must be fixed. Next, each trial can only have 2 outcomes. Now, as you're thinking through this 2 outcomes, typically success and failure is a good way to look at this. This isn't just that there's only 2 things can happen. So for instance, we'll eventually talk about how flipping a coin's a binomial experiment, but we'll also discuss how rolling a die can be a binomial experiment with 2 outcomes, success or failure. So many multiple outcome events can be written as a binomial experiment in terms of just having success or failure as the 2 outcomes we care about. The outcomes of each trial should be independent. Recall what we meant by independent with drawing cards. What we mean here is that the first event, the outcome of it should not affect the second event, etc. And the probability of success should remain the same for every trial. Again, think of flipping a coin. Getting heads the first time doesn't affect the probability of getting a heads the second time. The probability of success must remain the same for every trial. That's fine as long as you're using the same coin. Note that this doesn't have to be a fair coin. An unfair coin, where we are more likely to get heads or tails, satisfies all of these conditions if we fix the number of trials. Heads could be success. Number of trials are independent from each other and the probability is the same, even if it's not 0.5. So something like flipping an unfair coin would meet all of these conditions. The outcomes of the binomial experiments are called the binomial distribution. So that's how these experiments are distributed. Note that this is a very, very special case of the discrete probability distribution, and we'll discuss why we have a section on it later. First of all, some additional notation. So the probability of success in a single trial, this is not the probability of the sample space, so please bear with me. This is the probability of success, is termed P. The probability of failure is Q, and that's just 1 minus P. 1 minus P is the probability of failure, so you'll see Q sometimes. Sometimes you'll see 1 minus P. Both of these refer to the probability of failure. Little n is the number of trials. Recall this has to be fixed. X is the number of successes, this capital X. And the probability of X, this is the probability of getting exactly X successes. Now, this might not mean much now, but this word exactly is very important. We'll discuss it later. Note that the number of successes, think about if we flip a coin and we flip 10 coins and we consider getting heads a success. The number of trials would be 10 coins. X is the number of successes. X, the number of successes, has to be somewhere between 0 and however many times we tried. So if I flip 10 coins, I can't have 11 times getting heads or 11 successes. The number of heads I can get would have to be between 0 and n, and it could be any of these values. It could be any of these values. All right, given the above, the probability of any number of successes, any specific number of successes, exactly X successes, is given by this formula. Now, this formula looks really nasty. Remember, this beginning is just that n choose X. This is how many different ways that we can choose X in an unordered way. The probability of success to the power of the number of successes. So this is multiplying all of our success probabilities together. This is the probability of failure multiplied by the number of failures, or to the power of the number of failures. So this is multiplying all of the failures together, and this is the number of different ways that we can arrange them. You can write this in either way. Typically, you'll see it written out this first way. With n factorial, n minus x quantity factorial times x factorial. Please recall this is the probability of getting exactly x successes, exactly. So let's say we toss a coin 3 times, find the probability of getting exactly 2 heads. Note that little n is going to be 3 in this case. X is going to be 2. This is a coin, so the probability of success is on any single trial. So that P is the probability of success on any single trial, any single coin flip. That's going to be 0.5. It's the probability of getting heads or success. And then Q, the probability of failure, is also going to be 0.5. Actually, given that information, you could probably go on and try this on your own if you'd like to, giving this problem a shot. All right, working through this. We already know the answers, 0.375. We did this previously when we looked at the number of events and the number of outcomes in the event space, number of outcomes in the sample space. And this is a small enough problem we can write out by hand. And these are good ones to try out the first time. So remember, in the number of trials is how many times do we try it? How many times do we try flipping the coin? 3. In this case, X is the number of successes. How many successes do you have? In this case, we're interested in the number of heads. So heads is going to be called a success. So how many heads are we interested in? Well, we're interested in getting exactly 2 heads. X is the probability of success on any single trial. So this is important. We're calculating the probability of this many successes for the whole experiment. That's the whole problem. P is just the probability of success for a single trial. So don't make it too complicated. For a single coin flip, the probability of success is 0.5. For a single coin flip, the probability of a failure, now if heads is success, think about what failure is. Failure here is going to be getting a tails. So the probability of failure is 1 minus 0.5. That's also 0.5. Plugging in our values, we get 3 factorial divided by 3 minus 2 quantity factorial times 2 factorial times 1/2 to the second power, that 2, times 1/2 to the 3 minus 2, the first power. Plugging this into our calculator, we get 3 out of 8, or 0.375, which is exactly what we had before. This is exactly what we had before. Now note that we could write out the sample space and the event space in this case, but in many other examples we can't. So here's an example of kind of a word problem that we could see. Surveys conducted discovered that 1 out of 5 Americans says they visited the doctor. If we look at 10 people, what's the probability that exactly 3 will have visited the doctor? Note again this word exactly. We're not talking about less than 3 people or greater than 3 people. We're talking about exactly 3 people on the dot. Now, one of the interesting things about this particular one, we're interested in doctor's visits. So doctor's visit is going to be called a success. We're going to try out this with 10 people. So we're going to go talk to 10 people. That's our sample size. That's going to be little n. What's the probability of success? That is, success is going to the doctor. What's the probability that any one of these 10 people go to the doctor? Well, looking at this national survey says that 1 out of 5 people go to the doctor. So the probability that any person goes to the doctor is 1/5. Then we calculate the probability that they don't go to the doctor. That's going to be 1 minus 1/5. So looking at this, we get the probability of 3 doctor's visits is 10 factorial divided by 10 minus 3 factorial times 3 factorial. And then the 1/5, which is the doctor's visits, to the third power times 4 out of 5 to the 10 minus third power. Now this goes pretty quick, so let's break this down a little bit more so that we can track this. Now again, our probability of x is going to be n factorial divided by n minus x factorial times x factorial. I like this background. It reminds me of the beach. P to the x, and then we have q to the n minus x, and we remember p is the probability of success, q is the probability of failure. So I can write out a list here of what I need. The values that I need are n, I need x, I need p, and I need q. These are the 4 variables that I need to find in a word problem. And honestly, this is how I tend to focus on this. I tend to write out what all do I need. In this case, n, this is the total number of trials. So if I'm going to go talk to 10 people and I really don't know how many have been to the doctor, each person can be looked at as a trial. N is going to be 10. Now I'm interested, the problem said, in finding exactly 3 people who visited the doctor. I don't know why exactly 3, that's just what the problem said. So this is the value that I'm interested in. Note that if it said more than 3 or less than 3, I'd have to do 3, then 4, then 5, then 6. I'd have to add them all up. In this case, I'm looking at just 3. Now P, the probability of success for any given person. Again, this is where it gets a bit tricky. This came out of that survey. That survey said that 1 in 5 Americans said that they've been to the doctor. So for every single person that I go and ask, every single one of these 10 people, I'm expecting each one of them to have about a 1 in 5 chance of saying, yeah, I went to the doctor. Q, remember that original equation that we had, 1 minus P. This is going to be 1 minus 1 out of 5. This is going to be 4/5. Now, going back, once we have all of this information, this is where we get what's in the slide here, plugging all of this information in. Now I just type all this information in my calculator, and this is what spits out about 20%. So there's about a 20% chance that 3 out of those 10 people, exactly 3 out of those 10 people, went to the doctor last month. Now thinking about this, it's another word problem, but note that in this problem, reading through it, and you can pause at any time, but in this problem, we need to find the probability of at least 3 of these teenagers having a part-time job. So at least 3 is not just 3, it's 3 or 4 or 5. Now remember what we talked about in our probability chapter. Or means adding those probabilities together, because you can't have 3 and 4 at the same time or 4 and 5 at the same time. These are mutually exclusive events, so we can just add the probabilities without having to worry about subtracting anything. But we're going to have to find the probability for 3, the probability for 4, the probability for 5, and then add these 3 probabilities together to find at least 3. Remember, our equation only does 1 at a time, so we can only do the equation for 3, the equation for 4, or the equation for 5 at any one time. Looking at these values, again, we've got 5 teenagers that are selected. This is going to be our sample size. We've got 30% teenagers receive spending money from part-time jobs, so this 30% is going to be the probability for any single teenager, and then we're going to have to calculate Q from this. Go on and give this problem a shot if you haven't already. Pause and see what you can do. All right, so for the probability that we have at least, so that is 3 or more, we're looking at the probability of 3 plus the probability of 4 plus the probability of 5. Now these 3 probabilities we're going to have to calculate one at a time using our formula. So the probability for 3, we plug 3 in for x in the formula and we solve the whole thing. Again, at any time, feel free to pause once you feel like you're getting the hang of this and calculate the rest if you haven't already. Probability for 4, we plug 4 in for x and solve the whole thing. We plug 5 in for x and solve the whole thing. Note that our probabilities are getting pretty slim, but the overall probability of getting 3 or 4 or 5 means that we add the probability of 3, probability of 4, probability of 5 together. The probability of at least 3 is about 16% in this survey. Now there are tables that you can look up for these kinds of probabilities. We're going to typically not use them in these courses. Again, this is about the most complicated that I'll be asking you. So no need to use the table, though you can absolutely check it out if you're interested. And in the next chapter, depending on how far we get, there's some cool and clever ways that you can do this without having to use a table at all. Or by using a different table that is a little more common. All right, so why the binomial distribution and why are we making a big deal out of this? The binomial distribution has some really useful properties. So first of all, the mean is a very simple calculation. To find the mean of a binomial distribution, instead of doing that whole sum of x times the probability of x thing, I can just look at the number of trials multiplied by the probability of success on each trial. That's it. N times P, and that gives you mu, that mean. Variance, that big, long, complicated formula, the sum of x minus mu quantity squared times the probability of x. All of that is just n times p times q, the number of trials, times the probability of success on any single trial, times the probability of failure on any single trial. And again, remember, q can be written as 1 minus p. And the standard deviation is just the square root of this as before. But these are really, really useful and quick formulas that we can implement if we can identify it's a binomial distribution. The trick for these is you have to run down the mental checklist. Are all of these events independent? Do we have a fixed number of trials? Does the probability stay the same, etc.? And if it checks all the boxes of a binomial distribution, binomial, think about bicycle, there's only two outcomes, success and failure, then you can do this. So for example, let's try tossing 4 coins, find the mean, variance, and standard deviation. Again, this is something that we could do by hand. In fact, I think we might have done this exact example on a previous slide, or tossing 3 coins. But now we can see how easy this is. On any single trial, we have a probability of success of 1/2, and we have 4 total trials. So we expect to have 2 heads if we flipped a coin 4 times, which makes practical sense, and that practical double check is usually a good thing to consider. Now for the variance, we just add q onto this np, so we take this np, 4 times 1/2, and now q, the probability of a failure, the probability of getting a tails, 4 times 1/2 times 1/2 gives me 1. Finally, for my standard deviation, I simply take the square root of the variance and I get 1. This is how quickly we can calculate the mean, variance, and standard deviation of any binomial experiment. Let's move to a slightly harder case. It's not more computationally difficult necessarily, but maybe more ideologically difficult. This is a hard question for many students. Thinking about the number of 3s that are obtained in rolling a die, and at any time feel free to go on and pause and try to calculate the mean, variance, and standard deviation of this. But thinking about the number of 3s, you have to realize here that this is a binomial experiment, even though a die has 6 possible options. Because when we define 3 as our variable of interest, then this becomes a success and everything else becomes a failure. So we have success and failure. The probability of success is the probability of getting a 3. That's 1 divided by 6. The probability of a failure then becomes getting anything other than a 3. And you can go on and try that calculation on your own. What's the probability of not getting a 3? Just that 1 minus p if p is 1/6. So moving into the problem, mu, the n times p, or the mean number of 3s that are rolled, is 480, the number of trials, times our success on any single die roll on any single trial. That gives us 80 total 3s. We'd expect if we rolled a die 480 times to get 80 3s. Moving to the variance, we just add q. Note that q, the probability of failure, you can check your work if you worked on that, is 5 out of 6. There's 5 ways to not get a 3 out of 6, and if I multiply all these together, I get about 67 or 66.6 repeating as the variance of the number of 3s that I roll. And then I take the square root of this value and get 8.1650. This is the standard deviation of the number of 3s that I roll. Now remember this empirical rule that we had. How do we interpret this? How do we interpret this information? What does this standard deviation mean? And specifically, how do we use the mean and standard deviation to get an idea of what a reasonable range could be? So remember that the empirical rule said that 95% of the data is within 2 standard deviations of the mean. And this can be used with a binomial distribution approximately. In the previous situation, we had 83s, that was our mean, but then we said there was a variability there. So now what we're going to do is we're going to calculate a range that we'd expect 95% of these values to fall within. So in this case, from this empirical rule, we want 2 standard deviations below the mean, that's mu minus 2 sigma, and 2 standard deviations above the mean, that's mu plus 2 sigma. So what we're doing is we're using the empirical rule to say, okay, 2 standard deviations within the mean, that's fine, 95% of the data, that's fine. What are those numbers? What are those numbers of 2 standard deviations less, 2 standard deviations more? That's what this is in equation format. What's the number of 2 standard deviations less? That's the mu minus. The number of 2 standard deviations more, that's the mu plus. In this situation, we can plug in our mu and sigma. We get 80 plus 2 times 8.16 and 80 minus 2 times 8.16. And we find our range to be between about 63 and about 97. I'm rounding down here and I'm rounding up to make it a little bit wider. So there's, again, this is 95% from our empirical rule. There's a 95% chance that we would expect to see between 63 and 97 threes in our die rule. That to say, if we did this 100 times, 95 of them we would expect to see in this range, typically. And what this is more is if we did it an infinite number of times, 95% of the time they would fall in this range. So this is a nice, useful thing. In fact, the statistical term for this is called a confidence interval. If we have time, we'll get to this in Chapter 7. But these reasonable ranges can be calculated for a lot of statistics and tend to be this exact formula based on the mean, looking at the mean plus and the mean minus a few numbers to come up with a reasonable range of values for that mean. So in this case, a reasonable range of values for the number of threes. In this reasonable range, we can ask if this didn't happen. Let's say we had someone who was supposed to roll a die 480 times, and they came back and reported that they got 110 threes. Well, if 95% of the time they're going to get between 63 and 97, a value of 110 might be a little bit suspicious, might be a little far out there, and we might wonder if something weird happened if they were using a tainted die or maybe tried to get their data from somewhere else. Continuing on, let's try this one. In fact, why don't you go on and pause and give this a shot. All right, so we've got 2% of all American births are twins. If we have 8,000 births, what's the mean, variance, and standard deviation? So we've got the mean calculation is n times p. We have 8,000 births, that's our n. Probability of twins on any single birth is 2%. So in 8,000 births, we'd expect about 160, that's the mean value of twins. The variance here, we're going to take this and we're going to multiply this same number by 0.98 out of 100. 98 out of 100, or 0.98. And this gives us 156.8. This is the variability that we would expect in this value. We take the square root of this number and calculate the standard deviation. In fact, just like previously, we could use mu and the standard deviation to come up with a reasonable range for the number of births. That reasonable range, if you wanted to try it on your own, let's see, 25. So we might have something to the order of 135 to around 185 twins as a reasonable range here for the number of twins. All right, and this is the end. Now you have your journals. They aren't necessarily due a week from today, but they are on Blackboard, so please don't forget to do your journals. And in the next chapter, we'll be discussing the normal distribution and the central limit theorem, so you can look forward to that.